Hey everyone, we're going to learn how to deal with some more complicated circuits today. Typically they're called multi-loop circuits because they have multiple loops. You guessed it. And we have a physicist named Kirchhoff to thank for a couple of laws that lets us work these problems. The first one, this is sometimes called his first law, Kirchhoff's current law, simply says that in a circuit where there are multiple wires joining at a point, that point is called a node or a junction, and because of the law of charge conservation, I1, let's just say, I'm just labeling some currents here, I3, I4. Let's say all these currents are either going into or out of this point. Kirchhoff's current law says that the sum of the currents going in to a node is equal to the sum of the currents going out of a node. So it's pretty easy to write it down. You just look at which currents are pointing towards it. And so in my diagram that I drew, only I1 is pointing towards it. So I would say I1 equals, and then I2, I3, and I4, they're all going away from that node. I2 plus I3 plus I4. Bam. Done. You have used Kirchhoff's current law to write down a relationship among the currents at that node. The next law is a little more complicated, and this law is called Kirchhoff's voltage law. So let me show you a simple circuit where we can use it just to demonstrate what it would look like. So here's a battery whose EMF, let's say, is 10 volts. Let's say this is 100 ohms. Let's say that's 50 ohms. Kirchhoff's voltage law says that the sum of the voltage changes around a loop is 0. And to see how that works, you have to first pick a point, pick a starting point in your current, in your circuit. So I'm going to say I'm just going to start at A, and I'm going to go clockwise around this loop. Then pick a starting point and pick a direction to go around the loop. Next, you have to define a current for each loop or shared branch. And the shared branch part doesn't mean anything for this example, but when I show you one with multiple loops, the shared branch part will make sense. So when I say define a current, you must assume a direction. So I'm just going to completely sight unseen, I have no idea what's going to go on in this circuit. I'm going to assume the current goes this way around this loop, and I'm going to call it I1. Now this circuit is so simple that I could look at it and say, oh well, the battery, this side's positive, so I know the current's going to go that way. But in a multi-loop circuit like the ones we're about to see, you're not going to be able to predict things ahead of time. So I'll show you what it looks like if I assume that it's counterclockwise and then it turns out that it's actually not counterclockwise. You'll see what happens. 3, voltage sources are a voltage gain if you encounter the battery or the voltage source from negative to positive, or if you go across it from negative to positive when you're going around the loop, then it's a gain. So like up here, if I start at point A and I start looking for things and I'm going up counterclockwise, I encounter this battery, and when I go across it in this direction, I'm going across it from negative to positive, so that's a voltage gain because that's what the battery's doing for me. If you, oh, that's yellow. If you go across from negative terminal to positive terminal. Opposite, it's a voltage drop. If when you're going around the loop to find all the different sums or changes in voltage, if you encounter the positive side of the battery first, so if I'm going this way and I encounter the positive side and then I go across it, that would be a voltage drop. For a resistor, when I'm going around this circuit, if I encounter this, so I'm going clockwise around this circuit, and I see this side of the resistor first, and then I go across this way, that's actually opposite the direction that I drew my assumed current in. So like right here, I1 would be going from right to left, but I'm doing the voltage changes clockwise, so I go across this resistor from left to right. So going across this resistor in the opposite direction that this current is drawn is actually a voltage gain, because normally when current flows through a resistor, the voltage goes down. So if I'm trying to keep track of the voltage changes and I go across this resistor in this direction, which is opposite the way that I drew current, that's actually a voltage gain. Most of the time you're probably going to line up your currents and the direction that you do the voltage changes in so that resistors are voltage drops, but you will encounter resistors where it's a voltage gain sometimes. So we can summarize the rule as this. When summing voltage changes, if you go across a resistor in the same direction as the current, then that is a voltage drop, or negative. If you go across a resistor in the opposite direction of the current, that's a voltage gain, or positive. And when I say current, I mean the thing that you assumed. We still don't know if that's actually right yet, but when you work these problems, you make an assumption and you just work the whole thing like it's right. So, finally, let me write down the voltage changes. So the sum of the voltages around this loop should be equal to 0. I'm going to start at A and go clockwise. So the first thing I encounter is this battery. Well, I'm going from the negative side to the positive side if I'm going clockwise across it. So that's a voltage gain of 10 volts. So I just write down plus 10V. Then I get to this resistor and I go from left to right across it because I'm going clockwise around the loop. That's opposite the direction of the current that I assumed. And so if you're going opposite the direction of the current, that's a voltage gain. So I would put plus V, because I don't know what this is. And let me call this R1. Let me call that R2. I'll call that plus V1, the voltage across resistor 1. Then I'm still going. I'm going down here. I go across this resistor. This is still opposite the direction of I1. So that's another voltage gain. And I'll call that V2 for the voltage drop. I mean the voltage across R2. All those things should be equal to 0. We can use Ohm's law to replace V1 and V2 with an expression that uses the current that we drew. So Ohm's law for this resistor tells me that the voltage drop or the voltage change across it will be equal to I times R. So I can replace V1 with I1 times R1. And you can replace V2 with I1 times R2. And usually I'm going to write down this immediately and probably skip that line altogether, because the voltage change across the resistor is always, you can always calculate it with Ohm's law, and we always want an equation right here to work these circuits that has currents in them. So probably you're going to skip that first one and just write down the one with Ohm's law immediately. Now we're done with, that's Kirchhoffs voltage law for this circuit. There are actually no other loops, so we don't even need to use Kirchhoffs current law for this circuit. We could finish it and solve it right now because we have the numbers for R1 and R2. So this is 10 volts plus I1 times 100, that's R1, plus I1 times 50, that's R2. All that equals 0. So 10 equals negative 150 times I1. So I1 equals negative 1/15 amperes. And we are done. to show you that it is valid, you could find an equivalent circuit here by replacing these two resistors with one resistor whose value is, so these resistors are in series, right? So I could replace them with a 150 ohm resistor and it's the same circuit. That's 10 volts. So I equals V over R. I'm just using Ohm's law really quickly for this resistor. 10 over 150 equals 1/15 amperes. And we already knew, using what we know about circuits, that this is the plus side of the battery, so the current's going to come out of the plus side of the battery. So I equals 1/15 amperes going this way. And we could already solve this circuit. We didn't really need Kirchhoffs voltage law to do it. I just wanted to use it on a circuit that you could solve already, so that you could see what it looks like. But this negative sign that we got, the negative current means that your original assumption was backwards. The actual current is opposite from our assumption. But you should not go back. Like, don't go back and change the direction of this arrow, because if I come along and look at your work, I can see that you told me I'm assuming the current is counterclockwise in this loop, and then when you get a negative, that tells me that, oh, it was actually clockwise. But if you go switch this loop and then you accidentally leave this as negative, then I think that you think the current should actually be counterclockwise. So we didn't do anything wrong. That's just how you work these problems. You make an assumption, and then you stick with that assumption the whole time. And at the end, if it was actually the other direction, you end up with a negative current. All right, so let's work an example where there are actually multiple loops in the circuit. So here's an exam tip in SOCOS. It's like if you wanted a set of directions for these problems, you could use this. I'm struggling to resize this. All right. I'm just going to leave that over there. So here's an example problem with multiple circuits. Multiple loops. So let's say there's a 10 volt battery here, and there's a resistor here that's 10 ohms. Then there's a resistor here in the middle that's 100 ohms. And then there's another battery over here, which is 8 volts. This circuit is really difficult to solve using the techniques that you've learned before today. If you just try to use Ohm's law, it's pretty hard to solve this circuit. But if you use Kirchhoffs current law and Kirchhoffs voltage law, it's actually pretty easy to solve this circuit. So what I would do is first identify the loops. So here's a loop on the left, and here's a loop on the right. There's a lot of freedom you have when you pick loops, but generally, IB's not going to show you a problem with more than 2 loops, and usually you can just do left and right or top and bottom loop. I'm going to assume that this current is clockwise, and I'm going to assume also that this current is clockwise, just so you see what that looks like. Now remember, on the other page right here, right here, I said something about a shared branch. This problem actually has a shared branch. In the middle, this part of the circuit is actually in both loops that I've identified. So I have to create another current and call it I3 for just this part of the circuit. Here it's I1, here it's I1, right here it's I1, right here it's I1, but then I1 joins with current from over here, and it's something different. I2, I2, here's I2, here's I2, but then this middle is shared, so you have to define your own for that. Erase all these. And you can see now that there's a pretty easy way where we can use Kirchhoffs current law to get an expression that relates the currents. So you have to pick a node or a junction. So I'm going to pick that point and call it point P. So at P, sum of the currents going in has to be the sum of the currents going out. And so I1 is going in, and there's I1 going in. I3 is going out, and it looks like I2 is also going out from the way that I assumed all these directions. So that means I1 equals I2 plus I3. And then we'll just leave that there until we need it. Then we should pick a point here, point A, and we'll call that point B. So I'm going to do the sum of the voltages around the loop, starting at point A, and I'll go clockwise in this loop. That's got to be 0. So the first thing I encounter is this battery, and I go from the negative to the positive side, so that's a voltage gain. So that's plus 10 volts. Then I encounter this resistor, and I'm going across it in the same direction as what I called I1. So when you go across a resistor in the same direction as the current, that's a voltage drop. So I'm going to put minus I1 times 10 ohms. That's really the voltage across that resistor. I'm just using Ohm's law to replace it. Then I go down, so the left loop goes down next, and I go across this resistor in the same direction as I3, so that's another voltage drop, and it's I3 times that resistor, which is 100 ohms. And then I'm here, and there's no other components or devices, and I get back to the starting point. So I'm done with the loop, and I can say that all of those changes has to equal 0. Then you have to do the other loop. So the sum of the voltage changes around the loop, starting at B and going, I'll go around this loop counterclockwise just to show you can do it. So at B, if you go up, that's plus 8, and then there's no resistor here, and then I encounter a resistor here, so that's a voltage drop because I'm going down across it. So minus I3 times 100, and then there's no other components, and then I just say the sum of the voltages is equal to 0. So now we have basically what you end up with in these multi-loop problems is just a system of equations. These three things, and you're pretty much done with the physics at this point, and you just have to solve this system of equations in the 3 boxes. The right loop actually was pretty easy because there wasn't another resistor. So if you look at the right loop, I can immediately solve for I3. I3 is 8 over 100. Or, what's that? Well, I'm struggling. 4 over 50, which reduces to 2 over 25. Okay, 2 over 25 amps. So we found I3 immediately. And then you could take that and plug it in here. So 10 minus 10 I1 minus 2 over 25, that's I3, times 100 equals 0. That's 4, that's minus 8. 10 minus 10 I1 equals 0. 2, so I1 is 1/5, I think, if I did that right. Yeah. All right, and then we've got I1, we've got I3. We can find I2 by going up here and plugging in what we know. So 1/5 ampere has to be equal to I2 plus 2 25ths amperes. So therefore I2 is 3 25ths amperes. Did you catch that? I found that common denominator really fast in my head. Quick math. All right. At that point, we're actually done with the problem. Once you find all the currents, you're pretty much done with a multi-loop problem. So that's what one of these looks like. Just remember that when you go across a voltage source from the negative to the positive, that's a gain. If you had gone around the loop in this direction, that would be a drop. When you go across a resistor in the same direction as your assumed current, that's a drop. But if you go across the resistor in the opposite direction from your assumed current, that's actually a gain. Cool beans.